Hello viewers, we shall continue our discussion on interfacing of various subsystems that you require in the context of embedded systems. Today we shall continue our discussion on the interfacing of analog to digital converters and data acquisition systems. As you know, the world we live in belongs to analog domain, and most of the transducers generate data in analog form, and that analog data has to be converted into digital form before it can be processed by the microcontroller. So you require analog to digital converter for that purpose, and we shall discuss how ADCs work and what are the different types of analog to digital converters available. If you look at the block diagram, look at the function of analog to digital converters, you will find that there is an input, analog input, let it be represented by VA, analog input. This is your analog input, and it produces digital data. So analog data is the input and it produces digital data which is of n bits. Say this is your D0, which is least significant bit, and this is Dn minus 2 and Dn minus 1. Dn minus 1 is most significant bit. And so this digital data that has the value D is equal to Dn minus 1 into 2 to the power n minus 1 plus Dn minus 2 to the power n minus 2 plus dot 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 all the terms plus D0 into 2 to the power 0. So this is the digital data that you get here, and obviously it must have some relationship with this analog data, and the relationship is represented by VA is equal to nearly equal to K into D, where K is a constant. So the relationship between this analog data and digital data is shown in this diagram. Now the analog to digital converters are of two types. The ADCs that you normally use are of mainly two types. One is known as direct type, another is known as indirect type. Let's see what are the two different types. One is your indirect type, another is direct type. In the indirect type, usually the analog data is converted into some intermediate form. First it is converted to, the analog voltage is converted to some intermediate form, usually frequency or time period. Then this is converted into, so first it is converted into this indirect form, then it is converted into digital form. And the examples of this indirect type of AD converters is, for example, dual slope ADC. We shall discuss in detail. We shall discuss about it in more details. The dual slope ADC, which is very popular. So far as the direct type of ADCs are concerned, the direct type of ADCs are usually generate the digital data directly. So here you get direct data from the analog data, and the different types are number one is flash type, second one is counter type, third one is servo type, fourth one is successive approximation type, successive approximation type, and so on. So these are the popular types of direct types of AD converters. So we shall discuss about both the types of AD converters. Let us start with this dual slope AD converters, which are very popular. The dual slope AD converters, block diagram of a dual slope AD converter is shown in this diagram. Here, as you can see, the first building block is known as analog switch. So here is your analog switch, and the analog input is applied here, say VA, and you require a reference voltage Vref, which is of opposite polarity to that of the analog voltage VA. So if this is positive, this has to be negative, or if this is negative, this has to be positive. Why? It will be very clear very soon. And this is an analog switch. Analog switch because the input is analog in nature, so both these are analog voltages. Either the analog input or the reference voltage is selected with the help of this analog switch, which is controlled by this mode control selection. That means depending on this signal coming out from the control circuitry, it will select either this input or this input. And the second building block you will be able to recognize. This is the integrator. This is an integrator, as you already know. R and C decides the time constants of the integrator, and this is a comparator. Comparator can be considered as half digital, half analog. The reason for that is your input is analog here, but output is digital. Here the function is like this. If this is a negative input and this is a positive input, if the input on the negative input is higher than this, then output will be 0. On the other hand, if this input is lesser than this, the output will be 1. So depending on the relative voltage levels at these two inputs, the output can be either digital 0 or digital 1. And this is an AND gate, as it is clear. And this part, the clock generator, control circuitry, these are, we can consider them as the control circuit. And of course, you require, in addition to this, one end stage counter, which is controlled by this control circuitry. It can be reset, and if this signal is going out, going from the end stage counter and going to the control unit. This control unit has got two signal lines. One is known as SC. SC stands for start conversion. And EOC stands for end of conversion. So that means the conversion process, analog to digital conversion process, can be initiated with the help of the start conversion signal, and when the conversion is over, end of conversion signal is generated by this control circuit. Now let us try to understand how this dual slope ADC works. First of all, dual slope ADC will work in this manner. To explain the operation, let me draw the output of this comparator, output of this integrator. So initially, let's assume this this capacitor is fully discharged and output voltage is 0, and that time this analog input is connected for a fixed duration of T1. So as this input is positive, this output will go in the negative direction. So the output of the integrator will be like this. So this duration is fixed. Let's assume this is the duration. So this is the voltage. In this direction is the voltage, and this is the direction of time. So I am plotting the output of this integrator here. Now for time T1, where T1 is equal to 2 to the power n into t, where t is the time period of this clock and as you can see here, this is a n stage counter. So the maximum count value is 2 to the power n. So for the maximum count value time, this particular switch is closed. So this input is integrated and this output goes in a negative direction and it reaches up to certain level, let it be denoted by V1. So it reaches level V1. Now after time T1, the control circuitry changes the mode, and instead of connecting this one, so this was connected for duration T1, now this is connected. After time T1, this is connected and this is disconnected. So during this time, what will happen, the output will go in the reverse direction because the voltage here is negative. So the current will flow in the opposite direction. This capacitor will keep on discharging, and it will keep on discharging until it reaches the 0 volt. So here what will happen at this point of time, the output of the comparator will go high. So let me draw the output of the comparator. This is the output of the comparator. It will go high here and it will remain high, and as long as it remains high, this output of this and this comparator is 1. Now this clock generator is applied and at this point it is resetted. So at this point, because it is counting 2 to the power n, so it's counting with 0 here and it becomes 0 again here. Then again it starts counting. So again it starts counting from 0 value and it will count up to some value here. Now whenever this point is reached, counting is stopped. So at time, let this duration be represented by T2. So T2 is the duration for which the output goes from this positive voltage V1 and it becomes 0. Now let us try to find out the relationship between this time T2 and this voltage, analog voltage VA that is applied here. Now V1, this voltage will be equal to 2 to the power n into T, that is the time, into VA by RC, because it's a integrator. So RC VA by R is the current and this capacitor will be charged. So you will get this voltage. Now you can see here this voltage is same as this voltage, this voltage. So here it will be, this can be equated with 2 to the power n into this time is your T2, into Vref by RC. Now they will cancel out and ultimately we will get VA equal to Vref into T by 2 to the power n into n, assuming that n count has taken place. So actually during this duration there will be n count will take place. So this part, as you can see here, Vref, this time T, 2 to the power n, these are all constant. So this value, this n, is proportional to this analog voltage. Now at the output of this comparator, you are getting this count value. So here you will get the digital data. So here you get the digital data, and that will be proportional to this analog voltage V1, as it is relationship. From this relationship it is clear. So this is your constant. So we have seen that a dual slope integrator produces a digital data which is proportional to the analog voltage, and this particular analog to digital converter has been found to be very popular because it is simple, low cost, but there is a very important parameter which is known as conversion time. Conversion time is long conversion time, and because of this particular AD converter is not popular because of the slow conversion, long conversion time. Now let us focus our attention to the direct type of AD converters, which are in general faster. First we shall consider the flash type analog to digital converters. Flash type analog to digital converters, as you can see, requires a number of comparators. These are comparators, and this one is a priority encoder. So this is an priority encoder. Let us try to understand the operation of this circuit. Here there is a reference voltage Vref, which is applied to a voltage chain of resistors, which is acting as a voltage divider. So the voltage here, if you count the total number of resistors value, it is 8R. So what will be the voltage here? Here the voltage will be 1 by 16R, because this is the half R into Vref. And here what will be the voltage? Here the voltage will be, this is 3 by 2. So 3 by 2, 3 by 16 Vref, and so on. So in this way, these are the different voltages which are connected to the negative input of the comparators. Now let us see what will be these outputs for different input values. Whenever the voltage is above 1/16th of the reference voltage, then this will become 1. Whenever this is above 3 by 16th of the reference voltage, this will become 1. Whenever the input voltage is more than 5 by 16th of the reference voltage, this will become 1, and so on. So in other words, as the input increases from some 0 to Vref gradually, this will become 1, then this will become 1, then this will become 1, and ultimately it will become 1. So for voltage in between, say 0 to half Vref, we get 0. So we get all 0. All the 8 outputs will be 0. And from say half RF Vref to 3 by 2 RF Vref, it will be, this bit will become 1. Then whenever it is above this and up to 5 by 2 Vref, you will get 1, 1, and other bits will be 0, and so on. And whenever the voltage reaches Vref, then it will become all 1. And since this is a priority encoder, for this input combination the output will be 0, 0, 0. For this input combination the output will be 0, 0, 1, and for whenever all of them are 1, it will become 1, 1, 1. So we get an encoded output here corresponding to this. And you may be asking why it is called an flash AD converter. The reason is, as you can see, these devices, this priority encoder, the comparators, these are pretty fast devices. So the conversion time in this particular case can be as small as 1 microsecond conversion time. On the other hand, in case of your dual slope AD converters, the conversion time can be of the order of millisecond. So you see, compared to dual slope analog to digital converters, which are indirect type AD converters, this flash type AD converter gives you very low conversion time, which is of the order of 1 microsecond. So this is the internal circuitry of a flash type AD converter. Since the conversion is taking place very quickly, almost in a flash, that's why it is called flash type analog to digital converter. And in fact, the commercially flash type AD converters are available. For example, this is one flash type AD converter, and your data, your input can be, say, VA can be from, say, here you can apply minus Vref and plus Vref. So whenever it is equal to equal to say minus Vref, then the output is 0 0 in hex, and whenever Va is plus Vref, say it is equal to FF hex. That means this minus Vref can be 0 volt, and plus Vref minus Vref you can ground it 0 volt, and this can be 5 volt. So as the input changes from 0 volt to 5 volt, you will get digital data D0 to D7, which will change from zeros all 0 to all F. Now one point you must notice, in case of flash type of AD converters, the number of comparators is large. So for 3-bit analog to digital converter you require 8 comparators. For 4-bit analog to digital converters you require 16 comparators. For 5-bit you require 32, and so on. And for 8-bit you require 256 comparators. So as the number of bits is increasing, the number of comparators is increasing at a very rapid rate. That is why this flash type of AD converters is suitable for smaller number of bits, Usually say it varies from 4 to 8. AD converters up to 4 to 8 bits are available, and this particular flash type AD converter gives you this 8-bit conversion, which can be interfaced. This flash type AD converter can be interfaced through the port lines of 8051, and the interfacing is shown here. So you can do the control operation of this AD conversion. Conversion can be started by activating chip select and write. So whenever this chip select and write is activated, conversion is started, and with the help of chip select and read, you can read the data through this port 1, P1 to port 1, 0 to 7. These are the different bits. So these are the input ports, and these are the output ports. So these are configured as output and these are configured as input. So this is how you can interface one flash type AD converter. As I told, these are very fast, but number of bits that you can get is small, 4 to 8 usually. So flash type AD converters are becoming popular in many applications, particularly in situations where the number of bits that you require is not many. Now let us consider another AD converter, which is known as counter type analog to digital converter. The block diagram of a counter type analog to digital converter is shown here, and you will be you can see, in case of implementing analog to digital converter, we are using a digital to analog converter, which I have already discussed earlier. That is why I discussed the digital to analog converter earlier, because you will see that in implementing different types of analog to digital converters, we use digital to analog converters as the building block, as it is the case in this particular situation. Now here you require the building blocks, like this is a comparator, which I have already explained. This is an AND gate, and this is your binary counter. This is a binary counter, and of course this binary counter you can start conversion by resetting it. So this is essentially start conversion, and it can generate end of conversion whenever, not from here, actually end of conversion will come from here itself. This is your end of conversion, not from the counter but from this point. Let's see how it really works. This is where you apply the analog input voltage VA. Then we reset it, and as it is resetted, this count value will be 0. Now we apply the clock here. Since this input, initially this value is 0, so the output will become this DA converter, this counter value is all 0, so this value will become 0, and this will be 1. So, actually here this has to be positive and this will be negative. So, since this is positive input and this is negative input, I have applied a positive analog voltage. This input will be 1 and clock will be applied to this. And so, as the binary counter increases the value from say all 0, let us assume this is 8 bit, gradually increases, the here these are applied to a digital to analog converter. So, at this point how the voltage will change? The voltage at this point will change in this manner. At the output of the digital to analog converter, initially for 0 value this will be 0, then it will become then when it becomes 1, say 0 0 0 0 0 0 0 1, then it will increase by 1 step. So, in this way it will like a ramp ramp voltage, it will keep on increasing. Now, when it will stop? As this voltage becomes greater than that, that means whenever it reaches becomes equal to VA, let us assume this is the time and this is the voltage. Let us assume at this point this becomes equal to VA. So, the counting will stop here because the clock is not allowed to reach the count value, and whenever this output changes from 1 to 0, we know that end of conversion is taking place. So, at this point whatever is the count value, that is your proportional to the digital data. So, this this can be applied to some display to get the display of the digital data. So, this is how this counter type analog to digital converter works. The main problem with this counter type AD converter is that the conversion time is long conversion time. This long conversion time, because of this long conversion time, it is not commonly used, and in place of this two other different types of AD converters are used. Let us see what are the other two similar type of analog to digital converters that are commonly used. The second type of similar AD converters, this is rather third direct type analog to digital converter. Here you require, instead of a simple up counter, in the previous case this was a binary counter, but essentially it was a up counter. After it was initialized, start conversion, it was made 0, then up counting was going on. On the other hand, in this particular case, you use one up-down counter. Up-down counter. How up-down counting is done? You see, this is your clock applied to the up-down counter, and this is the analog voltage VA that you apply here, and this is the DAC, digital to analog converter. Now, let us see how it works. Here you can see here there is no need to reset it. For at any instant of time, whatever is the count value, corresponding to that an analog voltage is generated and applied to this output of to the input of the comparator. This is a comparator. Now, if this voltage is greater than this one, then this is 1. In that case, that means if let us assume, let me represent it by V DAC. If V DAC is greater than VA, then output of the comparator is 1. Comparator output is 1, and then we do down count. Because this voltage that you getting here is more than this, so you down count, and its point will reach whenever this count value will correspond to a voltage which is same as this one, and next point it will become lower than that, then it will do up count. So in this way it will keep on doing up count and down count. Let's assume the input voltage is changing slowly like this. In that case, the counter, this up down counter will keep on, here it will do up count. So in this way the output of the DA converter will keep on increasing, and here it will do this change, here it will go up and down, I mean up and down, and then it will do down count, and accordingly the output of the DA converter will change this way. So in this way it will keep tracking the analog voltage and corresponding digital value you will get here. That's why the servo type AD converters is also known as tracking type. Tracking type ADC. Main problem of this tracking type AD converter is that if the input changes very sharply, suppose the input changes like this, so in that case the counter will slowly reach, so it will not be able to follow the fast change of this analog input. That means when the input change is taking place slowly, then this servo type ADC or tracking type ADC is suitable and it can be used. And here also as you can see, if it is very close to the voltage, then it does not require much of conversion time. If you change the input slowly, this output will also change slowly and you can have some digital display here. So the conversion time is very small here if the input is close to the input that is produced by the DA converter. Otherwise it may take some time. So this is the servo type AD converter. However, the most popular type of AD converter that is commonly used in practice is known as successive approximation type ADC. The successive approximation type ADC block diagram is somewhat similar. Here also you require one digital to analog converter, you also require one comparator. What is different here in this case is a resistor. In this case this is called SAR. SAR stands for successive approximation resistor. Approximation resistor. What it does? The successive approximation resistor, this is not a counter. So here the conversion process is done in a little different way. You apply the analog voltage here, and initially say you start conversion with the help of this SC, and you get the end of conversion signal from the successive approximation resistor or the controller. Let's see how it starts, it does the conversion. The conversion is done the way the weighing is done. Is done in the SOPs, or you can say it is done based on binary search. Let us try to understand how it works. Suppose this is a balance. You want to weight something. Suppose this is the commodity that you are interested in weighting, and you know that the maximum value will not exceed, let's assume 16 kg. So the value, the weight can remain in the range of 0 to 16 kg. One approach is first to put 8 kg. So you first apply 8 kg, 8 kg here, middle one, and if we by applying there, if it goes in this direction, that this 8 kg is heavier than that, you remove 8 kg, then you put 4 kg. On the other hand, if it is heavier than 8 kg, then you retain 8 kg, then you put 4 kg, and after putting 4 kg, if this weight is still more, then you put say 2 kg, then you and if still if it is heavier, then you put 1 kg. So in this way, by putting 4 weights, you will be able to approximate up to 1 kg just by 4 steps, in 4 steps. And it can be shown that any weight between 1 to 16 kg, rather 15 kg, because if you add up 8 plus 4 plus 2 plus 1, these are the weights. You can it can vary from 1 to 15 kg. You can weight in 4 steps. This is the basic approach of successive approximation. First, you as for example, you want to find out something, some word in a dictionary. You first open in the middle of the page, middle of the dictionary. If it is not, depending on what is the word, you go either to the left or to the right. Similarly, for of that remaining half, you choose one of the two halves. In other words, at each stage, you are searching, or you are eliminating half of the search space. That is why you can call it, it is very similar to binary search. So, the successive approximation algorithm is very fast, and it can be used in many applications. Now, in all these cases, we have seen that we are using some special type of hardware, counter, up-down counter, or a successive approximation register and other things. Why not use the microcontroller or microprocessor to do this and realize AD converter? So, use of microcontroller to realize ADC. We can use one of the three techniques, counter type, servo type, or successive approximation type by algorithm. Let us see how it can be done. We use the same block diagram, similar type of block diagram. We use one DA converter. This is a DA converter, and output of the DA converter is applied to one comparator, as we did earlier. So, this is connected to, say, positive input, this is negative input. This can be connected to the analog voltage, analog input. Now, this input to the DA converter can be connected to the port of one microprocessor. Say, let it be connected to port 1 of 8051, and this let it be connected to port 3.0 of the 8051. So, with this hardware connection, you can realize one of these three algorithms, say counter type, servo type, or even the successive approximation type. How? By suitable algorithm. With the same hardware circuitry, say DA converter connected through a port, then the output of the DA converter is connected to a comparator, and this output of the comparator is connected to another port. So, with this hardware interfacing circuitry, you can realize different algorithms. Let me explain the operation of the circuitry whenever it is used to implement successive approximation algorithm. This is the successive approximation algorithm. So, this is where you start. You configure port 1 and port 3 as needed here. Port 1 has to be connected as output port, and port 3 has to be connected as input port, particularly the 08 bit of port 3. Then you clear accumulator, and another variable you choose, current bit, which you are setting as 7. Initially you are setting it 7. So, as you set this bit is 7, you go to the next step, then set current bit of ACC, set current bit of ACC. That means the accumulator will now have most significant bit is 1 and the remaining bits 0, and that is applied to port 1. So, here you will get most significant bit 1 and remaining bits 0. This is applied to the DAC. So, if the full scale voltage is 5 volt of the DAC, because of this application you will get 2.5 volt applied here. And after that you generate small delay, because this circuitry, as you know, takes some time. DA converter comparator will take some time to stabilize the outputs, and after application of this, this output is stabilized, you read the port 30 line. Is port 3 line high? You will be checking whether this is high or low. When it will be high? When this output is greater than this, then this output will be high. So in that case, if it is true, then the reset current bit of ACC, as I told that you will be putting the half of the weight and remove it if the quantity is less than the half of the weight. This is precisely what is happening with this operation. And then after resetting it, you check whether the current bit is 0 or not. If the current bit is not 0, then you go to the next step. In this case, whenever the current bit is 0, then it is yes, the conversion is over, and the content of the accumulator is holding the digital data that can be loaded in the memory, and operation ends here. On the other hand, if the current bit is not 0, then you make the current bit equal to current bit minus 1. That means initially it was set to 7, then it will become 6. That means next time you will be applying, you will make this bit 1. This bit may remain 1 if it is not resetted, because if it is no operation, or it may remain 1. So let me put X, and then you apply this signal 0 0 0 0. And in this way, in 8 steps, it will go through this step. In 8 steps, the conversion process will be done. So for 8-bit AD converter, it will require 8 steps. For 16-bit, it will require 16 steps. So in this way, the successive approximation algorithm is performed, and this is the flowchart of the algorithm. You can write a program, very simple program to implement this. And in fact, the writing program for this counter type ADC, or say servo type ADC, is simpler than the successive approximation. So in this way, you can use the microprocessor, use the processing power of the microprocessor to do the analog to digital conversion. Now, whenever you do this, the microprocessor remains busy in doing the analog to digital conversion, which you may not like. So normally what is being done, AD converter ICs based on successive approximation algorithm are available. For example, AD 570 is an AD converter which is based on the successive approximation algorithm. You can use it, and in that case directly the AD converter can be interfaced to the microprocessor. So this particular chip performs the analog to digital conversion, and in that case all the circuitry that I have shown here, is successive approximation register, DA converter, this comparator, and everything is fabricated within the chip, and you can communicate through these lines. These lines with these DA converter outputs, they can be connected to the port, and the start conversion and end of conversion can be connected to the port. In other words, you will require just the interfacing will be very similar to this one. You will require this kind of 3 lines and these ports, and then AD conversion is done here. So in this case also the conversion time is not very high, few microsecond, 8 to 10 microsecond, or even less nowadays. So we have discussed different types of analog to digital converters, but whenever you perform this analog to digital conversion, the input of the analog to digital converter may not be very stable. It may be fast changing. In such a case, what will happen? The accuracy of the analog to digital conversion will not be very correct. I mean, the accuracy of the analog to digital conversion will not be good. So in such a case, we have to use one circuitry known as sample and hold. This is the schematic diagram of a sample and hold circuit, which can be implemented with the help of two operational amplifiers. And it has been found that to the analog to digital converter, the inaccuracy is proportional to the highest frequency. So what this sample and hold circuit does, it will sample the analog input which can be applied here. So this is the analog input, then hold it and keep it constant when the conversion takes place. So it has got two modes. What are the two modes? Sample. In the sample mode, this switch is closed with the help, which is controlled with the help of this mode control switch, and then this input, whatever is the input that is available here, and because this is a voltage follower circuit and this capacitor is charged, and if the input is changing slowly, this capacitor voltage also will charge slowly. So in this sample mode, the output of this output follows input. On the other hand, after the sampling is over, in the hold mode, this switch is disconnected and capacitor holds this value and remain constant. So during the conversion time, the sample and hold circuit will be in the hold mode. So the output will not change. And whenever you choose sample and hold circuit, for example, nowadays it is available in the IC form. For example, National Semiconductor LF398A is a sample and hold circuit. Sample and hold circuit. You have to look at several parameters whenever you choose one sample and hold circuit. These parameters are acquisition time, how quickly the data can be acquired, then aperture time, how quickly the changeover takes place for sample to hold, then third is your droop. As I mentioned, during the hold mode, this output should not change, but this capacity, because of the leakage of the capacitor, there will be some change. So this is the change in the output per unit time. Usually it is very small. This parameter you have to see. Then feed through. Last parameter is feed through. Feed through, because whenever it is in the hold mode, this signal should not reach the output, but because of capacitive effect of wiring, the some output will reach this capacitor and it will go here. It can be very small, maybe 0.001% like that, feed through. So these are the parameters you have to take into consideration while choosing a sample and hold circuit. Now, apart from this sample and hold circuit, you will require another interesting hardware that is required, particularly when you are performing data acquisition from a number of sources. There is a possibility of using, suppose you are acquiring data from k different sources. So in that case, you will be acquiring data from k different sources, and you will require k analog to digital converters. But in practice, that is not required, because you can use analog to digital multiplexer. Analog to digital multiplexer works in this manner. So you have got one analog multiplexer which has got a number of inputs, say 8, and there is a switch. This is analog switch. So it can select one of the inputs at a time. Let's assume this is channel 1, this is channel 2, and this is channel, say, 7. And you can apply some input here to select one of the inputs at a time, and this can go to sample and hold, and then output of the sample and hold can go to ADC. This is how it works. And this type of analog multiplexers are available in the form of IC. For example, AD 7503 is 8 channel multiplexer which can be used to build a data acquisition system. So if you look at, you can build one data acquisition system by using separate the multiplexer. This is MUX, sample and hold circuit, and ADC which is connected through some port lines. These are the port lines with the help of which you can select a particular channel, and with the help of this mode control you can sample the data, and that is applied to the AD converter in the hold mode. The conversion is done, and with the help of the start conversion and end of conversion, the data is read by the through the port line to the microcontroller. This is how a data acquisition system can be built. Now, this kind of data acquisition system are available in the market. For example, all the building blocks, multiplexer, sample and hold, AD converter, these are all built in within a chip. For example, AD 363 from National Semiconductor is a data acquisition chip, data acquisition system chip. This can be used. However, there are some low cost circuitry also. For example, a cost effective 8 channel analog to digital converter is available. This is actually very popular. This is ADC 0848. This is a 8 channel AD converter. As you can see, you can connect 8 sensors, and this is the analog ground, and 8 sensors can be at a time can be connected, and within this chip you have got the analog multiplexer. However, here it is assumed that the input does not change fast. So, there is no sample and hold circuit here. So, this channel selection is done with the help of this MA0 to MA2 lines. That means channel select can be done with the help of those MA0 to MA2, 0, 1, 2. 3 signals are sufficient because you have got 8 inputs, and this is sensed whenever you select chip select and write. That means whenever CS and write is activated, this whatever is on this line, that on these lines, these are transferred to the registers within this chip, and with the help of these two lines, MA3 and MA4, the sensors, the number of sensors that you have connected can be configured in 3 different ways. For example, they can be in 3 different modes. It can be single ended, or you can have only 4 sensors. So, in that case, the other one can be connected in this way. These two are connected, then these two are connected, then these two are connected. So, you require essentially 4 sensors, and this is known as differential connection, and this is controlled with the help of these MA3 and MA2 lines. Whenever this is 0, 1, this is single ended. Whenever this is x0, this is differential. It can be pseudo differential also, where you will require 7 sensors and this is connected to ground. So, in that case it is pseudo differential. So, in this way you can connect a number of devices in this manner. So, to conclude, in this lecture we have discussed the different types of AD converters and various subsystems that you require to build analog to digital converters. Thank you very much.